session is one of the two sessions on fault attack on symmetric primitives. And this session will have two talks, and then after the after the break, there'll be a few other talks in the on the same topic. So the first talk that we have here, we have a curious case of missing speaker, but we are trying to see if like he'll be online, but in the meantime, we'll be having the video played. So the title of the first talk is RAFA, Redundancies Assisted Algebraic Fault Analysis and its Implementation on SPN Block Ciphers. The authors are Zihong Qi, Fan Zhang, Tiangxiang Feng, and Zhu Gong. And the online presentation is made by Zephyr Qi.
Hello everyone, my name is Zehong Qiu, currently a master student at ETH Zurich, and the work I will be presenting was done during my study at Zhejiang University, with the assistance of Professor Fan Zhang and other fellow students at his lab. First, let's briefly review the background of our work. There is an asset of cryptanalysis attempting to break ciphers. One of the most effective yet elaborate tools is DFA, differential fault analysis. This method was first proposed by Bonner et al. At 1997. In this setting, attackers have no access of the underlying data, but are able to choose the plaintext being processed and read the corresponding ciphertext. Moreover, as indicated by the term fault, the attackers could inject unknown faults during the encryption. Finally, one analyzes the correct and faulty pairs of ciphertext to deduce valuable information of the underlying key. The information is listed as a set of algebraic equations, and solving the system gives the attacker secret keys of the cipher. After reviewing DFA, we would like to briefly introduce an instance of DFA on a specific block cipher AES, which would also be the subject of our work. The structure of AES reflects the general idea of block ciphers of subdividing the encryption into the key expansion and round operations, which are comprised of either linear or non-linear bit operations. After injecting an unknown fault at a specific byte position, the fault of faulty bytes can be deduced via the determining process of DFA. To retrieve the key, Tunstall et al. First establish two steps of equations according to the relation of different byte values. Then, they carefully design a scheme to solve this system, making it way much better than brute forcing. Specifically, they achieve it by alternating the position of the for loops. The most arguable issue of DFA is that it is difficult to extend to other block ciphers, because block ciphers have different structures. The smart way of looping over the variables of one cipher may not be useful for another cipher. So why don't we forget about solution finding, but rather focus on establishing the system to be solved? By black boxing the solution process, we will be able to utilize the technical merits directly, making it both effective and generalizable. This method is known as AFA, algebraic fault analysis. Set solvers are often applied as machine solvers because they ran under extensive research. However, even though this idea is seemingly appealing, there are non-negligible problems faced by AFA. First, black boxing the solution process may hide important property about the ciphers. Second, even though extensive research has been done to improve set solvers, the set problem itself is still hard. In fact, there was no report of successful AFA on heavyweight block ciphers with a minor assumption. Sorry. Next, we will explain our motivation and the main idea of the paper. First, we would like to introduce a subtle conceptual transition. The problem of retrieving the keys can be modeled as CSP, constraint satisfaction problem, where the constraints are deduced from the unknown plaintext and ciphertext. This leads us to the research topic of transforming CSP into SAT. After this conceptual transition, I would like to mention several important results at the research of transforming CSP into SAT. First, Bjork et al. Proposed a rather counterintuitive point that increasing instance size may not increase the complexity of set solvers. They said that the determining factor is the number of primary variables, which decide the whole solution space. In the context of grid analysis, the primary variable are the keys, which are fixed throughout the attacking process. The second observation is that the determination of variables during the search process does not have to be sequential. For example, the output variables of a round operation may be determined first as well as the input. Therefore, by incorporating the inference constraints for both forward and backward operations, we could accelerate the set solvers. Finally, we want to quote that in transforming CSP into SAT, the combination of various encodings tend to accelerate the solution. We phrase this method as incorporating redundancies in our work, because one encoding is complete and enough for modeling the problem, and having other encodings at the same time has no influence on the solutions. Here are some examples of different encodings. Suppose X is a 2-bit variable. The direct encoding introduces 4 Boolean variables. Each X equals I is the Boolean value of X equals I. The other encoding introduces 3 Boolean variables. Each of them is the Boolean value of X less than or equal to I. The log encoding introduces 2 Boolean variables to express its bit values. Now, to justify our idea of incorporating redundancies, we'll demonstrate a toy example to show how it might be helpful to set solvers. Suppose we have the CSP problem Z equals X and Y equals not X. The naive set instance is the conjunction of 5 disjunctive clauses. By properly reordering the variables, we can say that the set solver will first try Z equals 1. Then it will decide that X equals 1 and Y equals 1. But then the value of not Y or not X will become 0, which is a confliction. Finally, the set solver will determine that Z equals 0. But what happens if we incorporate redundancies, which are implied by the original CSP problem? If we substitute the expression of Y into the expression of Z, we'll find that Z equals 0. And if we incorporate the constraint Z equals 0 to the set instance, the set solver will obviate the need for exploring the branch Z equals 1. Next, we'll take a look at the methodology of RFA. As stated before, since the primary variables are fixed, having more constraints and intermediate variables may not harm the solution process. Moreover, after explicitly expressing the intermediate states in the system, we are able to easily incorporate redundancies, which will be discussed in the following sessions. So if a state S0 goes through the operation F1, F2, and so on, the equation we put in the system will be Si equals Fi of Si minus 1 for all I, rather than the single long equation Sn equals Fn, Fn minus 1, and so on, F1 of S0. The first type of redundancies are discovered by exploiting the fold propagation. Suppose a byte fold is injected into the output of the A shift rows operation. We can obtain the figure of the fold propagation on the left. The folds before and after a linear layer are also linearly related. For example, if we denote the injected byte fold as F, we can find that the first column byte folds of the output of the A's mixed columns operation are 2F, F, F, and 3F, where the multiplication happens on the finite field. The folds after The folds after a nonlinear operation are not directly related to the ones before this operation. So we will introduce new variables to represent the folds. For example, after the 9 sub-bytes operation, the folds on the first columns are new variables big F0, big F1, and so on. Having constructed the diagram of fold propagation, we can now read the redundant information. First, for the clean blocks where the folds are 0, we can simply have that the intermediate states of correct and faulty encryption share the same values at these bytes. Second, for labeled boxes, we can express their values by the differences of correct and faulty states, and the linear relations within the folds are directly encoded into the left-hand side of these equations. Even though we have discussed the diagram of fold propagation in the context of AES, we would like to emphasize that it can be automatically generated when applied to other block ciphers. There are two basic ideas we have mentioned. First, the folds before and after a linear layer are linearly related. Second, when the fold before an S box is 0, it is also 0 after that. Otherwise, we just introduce a new variable to denote the fold after the X box. The second type of redundancies aims to utilize the behavior of set solvers that the values of the variables are determined in a non-trivial order. Because the variables both before and after an operation T may be decided first, we simply incorporate both the forward and the backward operations into the system so that the input Si is determined first. The first equation will be activated and Si plus 1 will be quickly found. If the output Si plus 1 is determined first, the second equation will be activated and Si will be quickly found. So far, we have finished the construction of our CSP constraints, and it's time to consider feeding them into the set solvers. Furthermore, because some set solvers such as CryptoMiniSet could take as input XOR clauses, we only need to worry about nonlinear constraints. There are two options. First is to construct linearization. Specifically, we will replace nonlinear terms appearing in the system with an auxiliary variable A, which makes the system consisting only linear constraints. To ensure consistency, we need to add additional CNF formula to reflect the definition of these auxiliary variables. Jovanovic et al. Introduced the following strategies in their research on algebraic cryptanalysis. When there are nonlinear combinations of desired structures, the last four strategies may help reduce the number and length of clauses. Otherwise, the standard strategy can be generally applied. The second option we would like to mention is the use of Bosphorus, which is credited to the work of Chord et al. This is an ANF to CNF converters that utilize several techniques such as XL, XSL, Rickenstein's ANF to CNF conversion algorithm, and Gauss-Jordan elimination. In general, this tool discovers implicit linearity and compresses its CNF formula. We want to highlight that it doesn't conflict our redundancies idea, because the redundancies have been incorporated into the CSP instance. Finally, we take a look at the results of evaluating RFA in different contexts. First, let's see the improvement of RFA over AFA. Since AFA fails on heavyweight block ciphers like AES, we need to fix the value of the first K bytes of the key to conduct experiments. And it can be seen that the RFA achieves significant speed up over AFA, especially when the difficulty of the problem increases. When K equals 13, the acceleration ratio reaches near 37,000. Second, we mentioned that in the option 1 of handling the nonlinear constraints, several strategies other than the standard strategy may be applied. We also conducted experiment on the use of linearizing strategies to justify this design. We can see that when all linearizing strategies are applied, as shown by the last row, the acceleration ratio reaches the highest point. Next, show that the main idea of our work, incorporating redundancies, is significant to improve the efficiency. If we do not introduce any redundancy while keeping everything else the same time, at the same, it will take 168 minutes to retrieve the key when 5 bytes are known. If we only introduce the forward and backward redundancies, it will take 51 minutes. If we only introduce the fold propagation redundancies, it will take only 2 minutes. If we introduce all of the redundancies, it will only take 0.59 minutes, which is hundreds of times faster than the original one. Furthermore, we'd like to highlight that RFA can easily make use of further known information. For example, if we know the fold is a bit fold, we only need to append the following and most one constraint to the set solver. The table records the performance of RFA with either options of handling nonlinear constraints on the different fold models. There are several interesting conclusions we can draw from the table. First, RFA is able to retrieve the key of the AS in a reasonable amount of time, which makes it the first variant of AFA successful on such a challenging text. Second, at all situations, RFA using phosphorus is more efficient than RFA using the linearizing strategies. The reason could be that phosphorus discovers implicit linearity and compresses CNF formula, and the set solver we are using, cryptominiset, also makes use of the linear equations, namely the XOR clauses. The third conclusion is that RFA maintains the flexibility of AFA. That is, when we know something about the key, when the key is non-zero, or when we know something about the injected folds, we only need to feed a couple of short clauses into the solver. Then the efficiency of the solver will be accordingly increased. For instance, when we know that the fold is a bit fold, the runtime reduces from about 10 hours to about half an hour. Finally, to prove that RFA is indeed a general method on block ciphers, we have conducted experiments on two other famous block ciphers. The first one is Serpent, which was proposed by Anderson et al. Serpent consists of 4 linear operations and 6 4-bit X boxes. Since the X boxes are 4-bit, we will inject nibble folds to maintain consistency with the previous experiments. Here, we use K to denote the number of bit values fed to the set solvers. As one can see, RFA again demonstrates tremendous speed out over AFA, and it could retrieve the 256 bit in 21 hours using only 3 unknown folds. The reason why we use 3 folds is that when only 1 or 2 folds are injected, there are so many candidate solutions that could pass on the given ciphertext. In the worst case, the set solver is expected to find all the candidate keys and verify them using the plaintext. However, finding all solutions is an even more challenging task for set solver. The second one is Speedy. It consists of 4 linear operations and 1 6-bit S-box. The difference between RFA and AFA is even more significant in this experiment. We can see at the middle of the table, when 60 bits of the key are known, AFA takes half a day, while RFA takes only 5.5 seconds. When no information of the key is known, RFA can also retrieve it in 1 hour and a half. Furthermore, as stated by Leander et al. In their proposal of Speedy, this block cipher is proved to provide strong resistance against differential and linear attacks due to the small uniformity and linearity of its S-box. Indeed, there is no known effective DFA on Speedy. That's all of my presentation. Thank you so much for your attention.
Yes. In case if any of the speakers or co-authors are online, please identify yourself. I see Terry online, so maybe we can have some questions. Are there any questions from the audience? So any questions from the audience? Let us just check. Terry, can you hear us? Still have 2 minutes. We can take a question. Or responding. All right. In that case, sorry, you probably have to email to the authors. So let's move to the next talk. The next talk is titled Fault Meter, Quantitative Fault Attack Assessment of Block Cipher Software. The authors are Kirti Kamalakshan and Tester Ribeiro, and the talk will be given by Kirti. Stage.
Hello everyone. So today I will be presenting our work fault meter, which does a quantitative fault attack assessment on block cipher softwares. So this is a joint work with my guide, Dr. Chester. So as we all know, fault injection attack is one of the most powerful form of cryptanalytic attack on cipher. Cipher implementations are highly vulnerable to this class of attack, where attacker can inject fault during the execution of a cipher and gets faulty ciphertext, and attacker make use of the correct and faulty ciphertext to retrieve the secret key. So fault can be injected in multiple ways, right? So fault can be injected during the execution of the cipher using like optical fault injection, voltage glitching, or it can affect the physical structural component of the hardware like raw hammer attack. So in this work, we mostly focus on like the differential fault analysis, which consider the cryptographic differential properties of the cipher. So moving to a simple fault attack, this entire talk I will demonstrate based on this particular toy cipher. So it has like, it takes 2 plain text bytes, P1 and P2, and it has like K1 and K2 as the key operation, and it performs some set of operations like say sub-byte mix column and so on. So if I inject a fault before the final round key XOR, says checkered 0 fault, the truth table changes as follows from the previous case. So this particular location, we can mark it as exploitable, which is a straightforward case because the key bytes is visible at the ciphertext, right? So there are multiple locations in this implementation where the fault can be injected, but all those locations may not be exploitable. So finding the exploitable instruction is a tedious task. So this is not a pretty new idea, right? Still, there has been a huge amount of work over the last 2 decades to determine the exploitable operations from different block ciphers. But still, there exists like new CVEs and CWEs, which are due to the improper handling of fault attack and improper handling of countermeasures and so on. So where are we lacking? To understand where we lack, we should know the attack success requirements. So the attack success requirements of fault injection attack, we group it as 3. One is the vulnerable instruction. So for, as I mentioned, fault can be injected anywhere, but it should be the instruction where the attacker injects fault should be vulnerable. So we should be able to get a proper faulty ciphertext to retrieve the secret key. And even if we inject a fault in vulnerable instruction, it should corrupt the instruction output of that particular vulnerable instruction. And the third factor is that the corrupted output should propagate to the ciphertext so that the attack is successful. So what is the current practice? The current practice is that like we take some cipher implementation and we inject fault on different locations of this cipher algorithm or implementation and determine whether we can leak some secret key information and so on. But this method is time consuming and it's a manual effort. And over the last few years, there has been some automated frameworks that determine vulnerable instructions from different levels of cipher implementations. So if we group this set of automatic implementations, we can classify it as three groups. The first groups that work on at the algorithmic level, which takes block cipher algorithm as input, and it gives you like the exploitable operations from block cipher algorithm along with the attack complexity. And some of the tools that work at the hardware level, which take the like hardware implementations of cipher, and there are like multiple set of tools that work at the software level. So where these tools lag. So all these tools gives you an output which is binary, either 0 or 1, which tells us that whether an instruction or an operation is vulnerable or not. So none of these tools quantify whether the attack is successful based on like the underlying hardware. So here we introduce our framework called fault meter that consider the algorithmic property as well as we evaluate it based on the underlying hardware. So for analyzing the results based on underlying hardware, we have used 6 different hardwares from 16-bit to 64-bit and RISC and CISC architectures. So let's see the factors like that I mentioned before, the 3 factors that are required for a successful fault attack. So the factors boils down to, so we are analyzing cipher implementation. So vulnerable instructions boils down to like the cipher algorithmic properties of the cipher. And if we want to correct the instruction output, it depends on the underlying hardware, and the faults needs to propagate to the output of the output, and that depends on the program structure. So technically our framework consider all these things for the evaluation. So let's see one by one. So for the first case, we need to inject like fault in vulnerable instruction. So we need to determine the vulnerable instruction. So for our toy cipher that we have mentioned before, so this is the say pseudocode of the toy cipher in C implementation also, and we have represented it in a graphical representation. This is the control flow graph. So what we want to correct is we have to correct the final ciphertext byte. So there are like multiple ways by which the fault can be injected, right? We can either inject a fault in this particular node, or we can inject a fault in XOR operation that can propagate through this set of instruction to the output. So there are like so many nodes where the fault can be injected. And we need to determine all these nodes. So all these red nodes we mark as vulnerable nodes. That means fault injected in any of these nodes can influence this particular ciphertext byte. So this is may not be like easy when you consider a bigger ciphertext like AES, which has like thousands of nodes at the implementation level. So we need to find the exploitable location. For this, we use a framework that takes source code of the block cipher as input, and it performs fault mapping that map the exploitable operations at the algorithmic level to that of implementation. And it does fault evaluation, which does a reverse data flow analysis on the control flow graph and gives you the set of operations that are exploitable. So this framework, FEDS, was published in CHES in 2020. So the high-level overview of FEDS is that it can map the exploitable locations from the algorithm to different implementations of the cipher. So the evaluation result of FEDS was a bit interesting. So we evaluated it on different implementations of AES, and the result shows that the percentage of exploitable instruction varies depends on the cipher implementation and not just depends on the algorithm. So this is a representation of how AES lookup table with 6.5% of vulnerable instruction. So we will be using this representation like later. So once we find the vulnerable instruction, the next task is to determine how the fault corrupt based on the underlying hardware. So for this, we have like three possible ways the fault can corrupt the output, that are like fault in the instruction, fault in data, and fault can alter the control flow. So if I take an instruction, so there are like multiple ways. So if I take an instruction, it has like opcode field and operand field. And the attacker can inject fault in any of these bits to change the instruction. Or it can corrupt the data or memory. That means like it can change the value of operands by modifying the data or memory, or it can alter the control flow of the instruction. Say it can jump from this particular path to some other path by altering the control flow of the program. So in this work, we consider this three possible way of fault injection and also with different fault injection like types from bit fault to byte fault. So let's see the three possible ways and how we have evaluated it. So for our toy cipher and for the graphical representation, suppose if we want to inject a fault in the shift operation of this particular instruction. So the output of the shift operation, whether it's corrupted or not, does not just depend on the instruction type. It also depends on the underlying hardware. So how it varies based on the underlying hardware, to analyze this, we have used 6 different architectures from 16-bit to 64-bit. So let's see a quick example of if we consider two architecture from this case. So for the first case, in the shift operation, I take MSP 430. It's a 16-bit architecture and it has like 2 fields, right? The fault can be injected, and this is the opcode field, and it has like the other field where operands and registers are represented. So for the demonstration purpose, we inject fault in the opcode field, and let's say we inject a 1-bit fault. So the 4 possible cases of fault that corrupt the output are as follows. And this 4 possible cases will give you like 4 different opcodes. And these opcodes are like valid opcodes. So it may not result in an invalid case because of the tight encoding of MSP 430. So if I consider a second architecture, say RISC-V architecture, the opcode, the operation depends on 2 fields. Either it depends on the function 3 field or the opcode field. So if I want to inject a fault in the opcode field, I can inject fault in any of these bits. So if I, so for the shift operation, this is the possible opcode bits that is considered for RISC-V 32-bit. And the possible way of injecting faults are on the first field is like 3 ways, and these results in a valid opcode. And on the other hand, there is an opcode field. And if we inject a 1-bit fault, there are like multiple ways, maybe like 6 or 7 different ways. And that result in valid opcode and invalid opcode. So what invalid opcode means, for RISC-V, for these set of opcode fields are not there in their encoding scheme. So if an attacker injects fault and it results in invalid opcode, so it's obvious that it will not propagate. It results in program termination. So from MSP 430 to RISC-V, it's clear that RISC-V will have like more invalid opcodes compared to the MSP 430. So this varies depends on the encoding scheme of the architecture. So this is not just the case. This is fault termination due to invalid opcode, and fault can result in valid opcodes as well. That may not be like result in a faulty ciphertext always. It can result in cases that fault does not corrupt the instruction output, which means that if it's an add instruction, and even if we change a bit or multiple bits, it can result in a case that the output remains the same. Or it can corrupt the instruction output or result in program termination. Say, for example, if we have branch instruction and the opcode remains valid, but it result in an invalid address where it branches, so it can terminate the program. And the final case is the fault completes the faulty output, result with faulty output, where we have like the opcode remains valid and the result is changed. So this fault can propagate to the output. So the attacker can make use of only the F1 case for a successful fault attack. So as I said, we have analyzed it on like 6 different architecture to determine how it varies based on RISC and CISC architecture. For this, we have designed a simulator framework that takes implementations as input. It compiles the implementation and runs it and gives you the correct output. And it also induces fault based on the underlying hardware, and it induces multiple fault from bit fault to byte fault, and it gives the faulty output. It can be like any of the possible cases from F1 to F4. And this is a bit time consuming process. After analyzing it on like 6 different architecture, so some of the interesting results are as follows. So we have analyzed, we have came to a conclusion that MSP 430 is the most vulnerable architecture out of the 6, as the encoding scheme of MSP 430 is like tightly packed. And comparing ARM and RISC-V, there is like no direct comparison, but if you consider 32-bit, RISC-V is more, ARM is more vulnerable than RISC-V architecture. So as I said, if we consider the F4 case where invalid opcodes, so invalid opcodes are very less in MSP 430 due to the tightly encoding scheme. And we have also analyzed it based on the arithmetic instruction, number of registers, and addressing modes, and so on. So one quick example is like if we consider arithmetic instruction type, arithmetic instructions are more vulnerable compared to the other instruction types. Say load and store instruction, and branch instructions are, of course, like leads to less vulnerability due to more program termination. So now we have got the results of from fault corrupting instruction based on the underlying hardware, and we can inject fault in memory or register, which is a bit straightforward. We can change the data contents, and the result says that it does not vary much based on 8-bit to 64-bit. And the third way of injecting fault is fault injected in program counter. So for the fault injected in program counter, we need the set of vulnerable instructions. Why we need the set of vulnerable instructions is that, so if we inject a fault in the program counter, it can either fall within the program's address space, or it can fall outside the program address space. So if we inject a fault in a vulnerable instruction, it can jump to another vulnerable instruction, which is like follows it or before it, or it can jump to non-vulnerable instruction. So if it jumps to a non-vulnerable instruction, this means that it does not propagate to the output because it's not vulnerable. And even if we change the program counter in such a way that it falls, it may not result in a successful attack. So we have like analyzed this on using our simulator tool by injecting fault in the program counter, and the takeaway from these 3 possible way of fault injection are as follows. So we consider an underlying architecture, and we have, so this graph shows for the toy cipher that I have mentioned, and the bar shows that fault injected in instructions are like more vulnerable, like kind of have a probability of 0.5, but fault injected in data are like have high success probability because it does not have invalid instructions. So we use this probability to our next phase, to fault propagating to the output. So to determine how fault propagate to the output, we need to consider the program structure, right? So here for this particular example, how it varies based on the program structure. If I inject a fault in this particular instruction, so this B value is maybe like it before it's not equal to 0, and even after fault injection, it results in such a case that it's not equal to 0. So the flow goes through this path, and there is no additional instruction in this particular path such that it affects the output. But where in the other case, if it result in B equals to 0, it can propagate through the other part, and there are like some set of new instructions that are executed and which can which can alter the output of the instruction. So how can we corrupt B? There are like multiple ways the B can be corrupted. Fault can be injected in this particular node, or fault can propagate from the previous node. To analyze this probability, we have divided the entire implementation into three groups. That is like fault propagation to data dependent instruction, fault propagation through memory, and fault propagation through control flow instructions. So for the first case, the entire cipher implementation, we have grouped the data dependent parts. Say for this is a sample example. So if we need to correct the final store operation in this path, there are like multiple ways, right? So fault can be injected in the first node and can propagate through the data dependent path of path, or it can be injected in instruction I for itself. So to compute the probability, we consider all possible case by which fault can be injected, and the probability depends on the fault corrupting instruction and fault propagating through the data. So here we have 4 different probabilities, and we consider the max case by which the fault corrupt the output. Why we consider the max case is because we want the higher success probability. On the other hand, like we have memory dependent instructions. So if I say memory dependent instruction, we will have a huge number of store instructions within a program. And if we want to, if a output of a store instruction is corrupted, then that means that there will be a load instruction that gets corrupted where it loads from the same memory address. So for this, we need to determine the load to store dependency within the implementation and find the probability within all this load to store. And the final case is the fault in the control flow instruction, as I mentioned in the example. So if we want to alter a branch instruction, it can either propagate to the truth path or it can propagate to the false path. So we have derived a set of equations how the branch can corrupt the output. And due to time constraint, I won't be explaining how we derive the equation. So that using like with this equation, we were able to determine on what probability output of if we inject a fault in a branch, it can corrupt the particular output. So finally, our fault meter framework stitch all these probabilities from 3 different groups, like data dependent instructions. Then we have memory dependent instruction, and we combine the probabilities, and it continues until we get a stable, like highest success probability on each nodes. So this is like we have injected fault on 2 different architecture, and we have how we have analyzed this is we have also simulated this fault using our simulation framework, and we have also done the comparison whether it's matching with the theoretical probability. So as we have propagated the probability to the output, like success probability, now we stitch all these things together to our framework, which takes source code of the cipher implementation as input. And we have our vulnerable instruction identification module that take cipher algorithmic properties of the cipher and which gives the set of vulnerabilities. And our fault exploitable quantification module quantifies the vulnerability and gives you the success probability by which the instruction can be corrupted. So this entire framework, we call it as fault meter. So we have evaluated fault meter on different block ciphers. So for the first case, this is the percentage of vulnerable instruction for AES 128-bit lookup table. So after the evaluation, the graph shows that how like it varies based on different architecture. So for TI MSP 430, we can see that it has more vulnerable nodes, like the success probability is high on TI MSP 430 and it's low on 64-bit. And apart from this, we have evaluated it on different implementations of AES and like Glyphia, Camellia, and so on. So the graph shows that the percentage of instructions and the success score. So from the graph, we can see that TI MSP 430 has more like around about 6% of instructions, which has success score above 0.3. And the lowest is for ARM 64-bit. And yeah, similarly, we have evaluated it on like other ciphers as well. And final graph shows the evaluation of ciphers on TI MSP 430. And the final thing is like now we have the success probability and how we can utilize this. For this, we have used designed a fault attack aware compiler framework. So why we need to tune the counter? Here we tune the countermeasure, and based on there always exists a trade-off between security and performance, right? So if an user need like security design device like electronic voting machine, they may need more security than performance. And on the other hand, for smartwatch, they need more performance than the security. So here we use our framework and fault meter framework and that tune the countermeasures. And we have developed this on LLVM compiler framework, and we tuned the countermeasure, and we have used redundancy based countermeasure for the use case. And this graph shows like how the result changes once we tune the countermeasure. So it varies, depends on how much security user need compared to the performance. So the final result shows that we have evaluated it on 5 different cipher implementations and different user input from 0.4 to 0.8. So the most least vulnerable is AES T-table based implementation, and we were able to provide better security to this implementation with less overhead. And most vulnerable in case of AES is a bit sliced implementation. And to conclude, we have designed an automated framework that can quantify the success of fault injection attack based on the underlying hardware. And to show and we show that the success probability depends on the cipher algorithm, its implementation, and the underlying hardware. And we have analyzed it on 6 different platforms, and of which TI MSP 16-bit is most vulnerable. And if we compare like 32-bit processor, ARM is more vulnerable than RISC-V. And on the other hand, for 64-bit, RISC-V is more vulnerable. And if we consider like cipher implementation, T-table based implementation of AES is more secure compared to the other AES implementations. Thank you.
Thank you, Kirti, for the talk. We have time for some short questions. We have one.
Hi, thanks. Very nice work. I have a couple of questions.
Sure.
About, could you give more details on the fault models that you described for instruction skipping? Because
Okay.
In the examples you show, it's single bit fault and operand or the opcode. Did you also consider multi-bit faults in your evaluation?
Yeah, we consider like byte fault. It can be like bit to byte, any byte.
Okay.
Yeah.
And I was also surprised to see, well, it's not surprising, that the arithmetic operations are less vulnerable or more vulnerable than the loads and stores.
Yes.
But what happens in practice? Like, did you also compare it with the experimental results? Is it similar when you do it? Because when you look at the instruction level, it's possible that the arithmetic operations could lead to less successful glitches, but in practice, it might be other way around, and that could change the overall result.
Okay. We have done the experiment using our simulator tool. So we have generated random programs and like the results are from that. So we came to a conclusion that arithmetic instructions, like for us, it was giving like more vulnerable success probability compared to load and store.
And does it also match the experimental results?
No, we haven't done comparison like experimental. This is the experimental result.
Okay.
Yeah.
Yeah, and in the program control flow modeling,
Yes.
what kind of instructions did you consider as vulnerable? Is it only the, for example, if for jumps, or even register like loads and stores as well?
So the instructions that are vulnerable is determined by the first phase called feds. So feds can give you like the set of instructions that we need to consider as vulnerable instruction. So if it marks a load and store or branch instruction as vulnerable, then we consider it for fault propagation.
Okay, thank you.
So I would recommend we take the next question offline because we are already into the coffee break. So let's thank the speaker again. And now we have a coffee break, and I think we'll be back again at 11 with the next part of this session.